So our definitions for Arrhenius are easy. We've seen them. An acid gives me H plus, a base gives me hydroxide, OH minus, and we saw in neutralization reactions, these come together. So an acid and base come together to produce water. And that's why we called it a neutralization reaction. The Bronsted-Lowry definition is a little bit different. It's similar, but it's different. Basically, an acid, instead of them saying it dissociates or releases a proton, they call it a proton donor. And then a base, it doesn't necessarily have to give me hydroxides in solution. As long as it accepts a proton, it's considered a base. So the Bronsted-Lowry definition is a little trickier. So the focus on this definition is on the transfer of H plus ions. So there's really, on this, there's not really a dependence on aqueous solutions, but typically you do see this in water solutions. So the other thing that's trickier is with Bronsted-Lowry definition, you can't just look at the reactants. Like in the Arrhenius definition, we could look at the reactants and we could easily identify acid and bases. With Bronsted-Lowry, you have to look at the entire reaction to notice who is giving up the proton and who's going to accept it to identify which one's the acid and the base. So it's a little bit trickier for sure. So you can't have one without the other. You have to have an acid with a base. So acids donate a proton, bases accept them. So if I look at this particular example, right? If I throw HCl in water, okay, what happens is this is my chloride ion, and here is my hydrogen. Now, actually, what it turns out is, you know, there's a set of lone pairs on this water molecule, and the chloride and the hydrogen in hydrogen chloride have a bond, and in this bond there's 2 electrons, but the chlorine is more electronegative. So when I throw this in water, chlorine takes the hydrogen's electron. So now all I have is a positive charge. That positive charge sees this lone pair and it forms a bond with it. So what I end up getting is what's referred to as the hydronium ion. And the chloride is happy in solution as a negatively charged chloride ion because it took hydrogen's 1 electron to form an octet. So this is what acids do in water. They break apart and give me protons. They're basically proton donors. That's what an acid is. So who donated the proton? HCl, hydrogen chloride. In water, we would call that hydrochloric acid. Why hydrochloric acid? It's binary, so it has a hydro prefix. Why is it the Bronsted-Lowry acid? It donated a proton. But what's really interesting here is normally we would never think of water. We think of water as being neutral, right? But in this case, the water accepted its proton. So that made the water the base, according to Bronsted-Lowry definition. But it's hard to see this because you have to look at the whole reaction. You have to see where the proton went. And the proton went from the HCl to the H2O. Now, what would happen if I had ammonia in water? If you take a look, right, and I tell you already what's happening. I'm going from an NH3 to an NH4 plus. What does that mean? One of the hydrogens was accepted by the ammonia. There was an H plus transfer. And what do I end up getting? I see that an H plus transferred because if you look at NH3 plus an H plus would give me an NH4 plus. And if I take H2O and I subtract an H plus, what's left? An OH minus, right? So what do I end up getting? Ammonia is my base. Why? What did it do? It accepted the proton. But what's really interesting here is water, in this case, behaved as an acid. Why? It donated the proton. So in the last slide, right, in this slide, water behaved as a base. In this slide, water is behaving as an acid. Why? Well, it depends on what water is next to. If water is by a base, it behaves like an acid. If water is by an acid, it'll behave like a base. So water is considered what's referred to as amphoteric. Amphoteric means it can accept a proton or donate it. And water's, it's one of the unique, bicarbonate does that, bisulfate, but it's one of the few unique species that can do that. So with Bronsted-Lowry, it's really tricky. I mean, you gotta be able to recognize what's the acid and the base. So there's something called conjugate acid base pairs, okay? So if I look at hydrofluoric acid, right? And I see that it donates a proton to something, all that's going to be left is F minus. So the acid, once it does its job of donating a proton, because that's what acids do, whatever's left behind, once I remove that H plus, so in the case of HF, if I remove H plus, the hydrogen's leaving an electron behind, I get a fluoride ion. That fluoride ion is called the conjugate base. Once the acid does its job and donates or gets rid of a proton, it becomes a conjugate base. Now, you could look at it as, well, with water, what happened with water? It actually gave this proton to water. So water, remember, it accepted that proton. And we know that because over here, it went from H2O to H3O plus. So we added an H plus to H2O. So by water accepting that proton from HF, because really you could think of it as these two are interacting, that made water a base. And if water is a base, once it does its job of accepting that proton, the new species after it accepts it is called the conjugate acid. So the acid, once it does its job and donates a proton, is a conjugate base. The base, once it does its job and accepts the proton, becomes a conjugate acid. So with Bronsted-Lowry definition, you see you have to have an acid and a base to be able to identify them. They can't be separate. And you have to look at both sides of the reaction to identify it. So what's going to help you is by identifying what are called conjugate acid base pairs. So the HF and the F minus are conjugate acid base pairs because the only difference is a H plus, right? The other conjugate acid base pair is the water and the hydronium. Why? The only difference is a H plus. The difference is in the direction, right? So from the HF, we go to an F minus. That's how we know it's an acid, because it donated. The H2O goes to a H3O plus. So we know that this is a base because it accepted the proton in the transfer. And that's essentially what you have to do with Bronsted-Lowry definition. You have to look at both species in both sides of the equation, the reactants and the products, to see where does the proton go. So for each of these, can you write the conjugate base for the A's, right? And then can you write for the B's the conjugate acids? So what would be the conjugate base for hydrobromic acid? We know it's an acid, we see it in the name, but
Br.
Br minus, right? Because there's also what in solution? The proton. Does that make sense?
Mm-hmm.
So what about for hydrosulfuric acid? What would be the conjugate base? This was the first polyatomic ion I introduced you guys to when we talked about binary acids, to help you understand how they were held together covalently.
Sulfur.
Hydrogen sulfide. Look at your notes. Go back. Go way back when we were face to face. Remember that? When we were face to face, the first polyatomic ion I introduced you to was hydrogen sulfide, to show that a polyatomic ion is a species that is covalently bound. That's why it's held together, but it has a charge, and that's why it's an ion. You can go look back. Anyways, what would this be? It's not carbonate. It would be
HCO3 minus.
yeah, which you guys just had a lab on this, right? With your gas laws. It's called bicarbonate. Or you can call it hydrogen carbonate, right? So the conjugate base for hydrobromic acid is bromide. What did I do? I just took away an H plus. That's all I did. For sulfuric acid, hydrogen sulfide. For carbonic acid, hydrogen carbonate or bicarbonate. So now let's look at the bases. What are we doing for the base? The base doesn't donate a proton, it does what?
Gains.
Yeah, so what would HNO2, by the way, this ion, what's its name?
Nitrate.
Nitrite.
Nitrite. Nitrate is not on the 4, so it has 3. 2 is 1 less than 3, so it's nitrite. It's okay, Andrew. Good job participating. Thank you for doing that, man. I appreciate it. And you're doing it without even seeing us, so thank you. So this is nitrite. What's going to be the conjugate acid?
HNO3 minus O2.
HNO2, right? Because the nitrite gives me the nitrous acid. So people might go, well, where's the charge? Where's the charge? Remember, if I add an H plus, a plus and a minus give me a 0 charge. That's why there's no charge. What about ammonia? What if I add H plus to that? What's going to be my conjugate acid?
NH4 plus.
Excellent. What about OH minus?
H2O.
H2O, but remember, I told you guys, this is why I like HOH. It helps me balance it, but it also helps me understand the conjugate acid base pair that you would be seeing in chapter 10. So we already did this. You guys did great. So in reactions, can you identify the acid and the base and then the conjugates of each? So take a second. I really want you to try this. I can't see if you are, but take a second and try to do this, and then we'll go over it together. So for this, I want you to, on the left side, for each reaction on the left side, look at what happens by looking at the right, and then on the left side, tell me whether it's the acid or base based on whether it donated or accepted a proton. And then on the right, tell me the conjugate. Okay, let's start with letter A. Which one of these in letter A would be the acid. So we look at the left side.
H2SO4.
Yes, sulfuric acid is the acid. And water would be then what?
The base.
The base. Why? Well, this is doing what? It's adding an H plus to water. How do I know that? Well, H2O went to H3O plus. So it must have gained an H plus. So it accepted a proton. So that must be my base. So H3O plus must be what? The base becomes what?
The conjugate acid.
Excellent. The base becomes a conjugate acid. So what is bisulfate? HSO4 minus.
The conjugate
Okay,
base.
H.
The acid, H2SO4, once it donates a proton, becomes what?
The conjugate base.
Excellent. So the reason why the Bronsted-Lowry definition is harder than Arrhenius is because you have to look at the whole reaction. What about in B? What's happening here?
H2O is the base.
Is H2O accepting a proton? So does it accept a proton?
Oh, sorry, it's donating. I meant it was the acid.
It is the,
Giving.
yes, good. It's the acid. Why? Because we see that the proton is being transferred to this bicarbonate, because over here I just have an OH minus, and now the HCO3 minus becomes an H2. So water here, so over here water was behaving as a base. Why? It's in the presence of an acid. Here water is behaving as an acid. Why? It's in the presence of a base. So whoever water is around is how it acts. Isn't that kind of how people are? You act different around different people.
It
Right?
adapts.
Yeah, exactly. That's a good way to think of it. So if water's around an acid, it behaves as a base. If it's around a base, it behaves as an acid. So the acid becomes the conjugate base, and the base becomes the conjugate acid. Now there is a mistake in this PowerPoint. This should be a double arrow. Does anybody know why
Because
that should be a double arrow?
Dissociate and
What does the double arrow mean? Anybody?
it's at equilibrium.
Can go forward
It's-
and backwards.
Yes, it's at equilibrium. It can have the forward and the reverse reaction. Perfect. That's exactly right. So this can have both reactants and products. It's at equilibrium. And we'll see the reason why it's at equilibrium is because conjugate acid is a weak acid. It's not a strong acid like the sulfuric acid, which completely dissociates. That's why in A, the one direction arrow is actually correct. This is going in one direction, but B should have a double arrow to show that I can have the reverse and forward reaction. So they kind of show, you know, oh, so yeah, the 8, you can't see that, I'm sorry. It's because we solved it together. I forgot that I had it on the overhead, but I like to solve it with you guys so you can kind of see. But that just basically shows you what we just did. All right. Although they moved the HSO4 on the PowerPoint. There you go.
So it'll have double arrows only if it's a weak acid or weak base.
Yes. Yes. And that's playing into where we're going right now.